Hello and welcome to everybody on Cloud Fitness. So in today's video, we are going to see what is ElasticNet regression. We are going to understand this particular topic because again, when we do hands-on and where we have to set up this particular parameter of ElasticNet, that time you should know what exactly it is about. So before moving ahead, I do recommend all of you to connect with me on LinkedIn and as well as on Instagram, and I'm going to leave the link in the description box. So when you talk about ElasticNet regression, right? I have already made the videos on the linear regression and you already know that this is the cost function that we try to minimize with the linear regression, right? In the linear regression, what do? We create a best fit line, right? The equation is basically theta1 plus theta2 of xi, right? And y is the output, right? And this is just equivalent to your y is equals to mx plus c. We try to get the best fit line and we try to minimize this particular cost function, right? This is what we try to do as part of linear regression. But we also have studied the ridge and the lasso regression, right? We have understood the L1 regularization and the L2 regularization, which is nothing but your ridge and the lasso regression. In that, you already know that what we try to do, if you have this best fit line that you get y is equals to mx plus c, we try to introduce lambda, your slope square or the mod of your slope, right? This is the extra parameter that we try to add, right? This is the extra penalty. This is the penalty, right? We have already discussed this in detail in the previous videos, right? This lambda is nothing but the hyperparameter. This beta j is nothing but the mod of the slope, and this beta j square is nothing but the square of the slope, right? This is what we try to add to the cost function, which is also called as penalty. Now this is done to resolve the problem of overfitting, underfitting, to resolve the problem of overfitting and as well as for the feature selection, right? Now in this N1 and L2 regression, what do we do? So if we have equation like 2.5 x1 plus 30x2 plus 50x3, right? This can actually be reduced to, your 2.5 can be reduced to 1.2, your 30 can be reduced to 2.5, 50 can be reduced to 5. If you introduce something called as penalty factor, let's say 0.6 over here. Now this penalty factor is nothing but your lambda beta j modulus or square, depending upon whether you are selecting L1 regularization, which is lasso, or the L2 regularization, which is ridge, right? This is what we try to eventually do. Now there can be a situation where you want to do both, right? Then that particular part is called your ElasticNet. So in the ElasticNet regression, it is nothing but it is a regularization technique that combines the penalties of both L1 as well as L2 regularization. So you can see in this equation the cost function remains the same. You know, your lambda 2 beta square, which is nothing but your slope square, or the modulus of your slope, right? That is what you try to add. So here what you are trying to do, you are adding both L1 as well as L2 regularization terms to the linear regression cost function. So the cost function is actually same, right? But you have added both L1 and L2 regularization. So this is nothing but this is called your ElasticNet. So whenever we try to develop any model and whenever we want to make sure that we do both the regularizations, then in that case we go for ElasticNet regularization or ElasticNet regression. Now here we basically in terms of code, we try to add it as a parameter, we define it, right? Now when we define it, that time I will not be able to explain you the full theory, right? That is why I'm making these pre-videos for you to understand before I jump on to the hands-on. Now also remember that for this lambda and beta j, lambda and the slope square, or lambda or modulus of the slope in case of lasso, right? You can always remember that if you try to plot this cost function with respect to your theta or the slope, you have this gradient descent, right? This is the U-shaped curve that is formed. Now if your lambda is 0, this is the curve that is formed. Now the moment you try to increase the value of lambda, right, which is the hyperparameter, let's say 5, and then you have 10 over here. Now what happens is you can see how the curve is happening, right? The lambda is increasing and your theta, your slope is decreasing. That is exactly what will happen here as well. Now in this case, in case of ridge, right, this one is basically for your ridge algorithm, right? This particular cost function is coming from your ridge, and this one is coming from your lasso. So you can actually see that in case of ridge, what will happen is the slope will never become 0. The slope will always be there. It will become close to 0, but it is never going to get exactly 0 over here. But in case of lasso, if you look at the curve over here, as your hyperparameter increases, it is little flat over here. So there is a possibility that it can become 0. So this is also one of the difference between your ridge and lasso. So when I say that it can become 0, again, if you see what will happen is, in case of lasso, your slope can become 0. So if you are trying to reduce, right, let's say 2.5 to any particular value over here, right, by introducing a penalty factor in case of lasso, what can happen is this 2.5 can become 0 in case of lasso, but it will not happen in case of ridge. Now due to this, what happens is, if your feature x1 is not that important, it will be reduced, right? So this is also one of the difference between ridge and lasso. I just re-explained it in this particular video as well. But remember that for you to understand this particular video, you should make sure that you have already covered my previous videos. That is when this will make more sense to you. So I hope you like this particular video. Do remember to like, share and subscribe to my channel, and do let me know in the comment section if you want me to describe any particular topic in detail as well. So thank you so much for being till here.